Thanks for the introduction. So today I'll present our work on unveiling Heisenbugs with diversified execution. I'm a PhD student at Carnegie Mellon University. Debugging embedded system software is challenging, especially in the presence of non-determinism and interrupts. You might often be able to relate to the situation where you insert breakpoints in your code only to realize a bug that you were chasing now disappears. These quirky bugs are often called heisenbugs because they almost magically elude any attempts to reproduce them through debugging. While this is just a simple example though, heisenbugs plagued embedded deployments at scale. If you consider typical deployments, you often run static analysis tools followed by hardware-in-the-loop simulation testing with intense dynamic analysis bug detection techniques. But when you finally deploy these systems in the wild, they're running across millions of diverse platforms in unpredictable physical environments. Thus, due to complex edge cases, it's no surprise that these often encounter bugs. The problem is, due to the real timeliness and the limited compute available on these platforms, they're unable to add debugging capabilities or logging mechanisms into these systems. And when they're finally brought back in-house to debug, you're unable to reproduce these bugs. So we asked the question, is it then possible for us to instead detect these heisenbugs at deployment? And to do this, it's useful for us to ground ourselves in a specific concrete bug example. For our paper, we considered dynamic data race detection using a simple technique called trap delay injection. So this technique is quite simple. Here we have two concurrent threads accessing various memory addresses through loads and stores. The goal here is we insert probes on each of our memory accesses. And in each of these probes, we essentially check whether we have simultaneous accesses to the same memory address during a fixed delay window. If there are two accesses to the same address during a fixed delay window, and at least one of them is a write, you can say that this is a data race. And this is a technique that underpins a few successful tools available in both industry and research, like Data Collider and TSVD, which has been deployed at Microsoft for CI testing. But now we want to ask, what do data race heisenbugs look like? And this is quite interesting. So we ran an experiment where we took a program, ran it across different devices, ran it across different levels of debugging instrumentation. So what we did is we took all of our possible memory accesses and chose a random partial subset of memory accesses to instrument, and then ran them stochastically across thousands of runs to see what that distribution looks like. For ordinary bugs, you see this sort of expected behavior, which is that as we increase our debugging instrumentation, we're more likely to detect this bug. And this is because we're more likely to instrument the bug. However, for heisenbugs, this is quite surprising. What we see isn't this. What we see is that there are specific operating points at which bugs are increasingly more detectable. And more interestingly, this is not at the maximum instrumentation density that you expect for typical ordinary bugs. And so this brings us to our first non-intuitive observation, which is that there's no single instrumentation level on a device that's optimal for heisenbugs. In particular, even the maximum instrumentation is not optimal. But this observation goes a little deeper. Consider this program that we ran our data race detection algorithm on. It's not important what this program does, but we have found 6 data race bugs in this program. And we've highlighted 2 devices here, one, the compute stick in pink, and the NUC 11 in red. The interesting thing here is even though the compute stick is a weaker device, it's actually a much more powerful bug detecting device. As you can see, the NUC is essentially incapable of detecting any of the bottom 3 bugs. And so this brings us to a second non-intuitive observation, which is that more computing power doesn't actually imply that you're a better bug detection device. And so using these 2 observations, we propose a hypothesis towards embedded debugging at scale that hinges on 2 ideas. The first is this idea of stochastic partial instrumentation. So this is the idea that we sample a subset of our whole instrumentation space. We will sometimes call this instrumentation density. By doing this, sampling the small subset, we're able to decrease our overhead by not instrumenting all of our memory accesses, but we're going to decrease effectiveness because we may not be instrumenting the bug that we hope to find. But then we ask, if we couple this with diversity at scale, instrumenting partial stochastic subsets across millions of devices, will we be able to compensate for this effectiveness? And so this is what we look to study with our system called Beanstalk, which is a scalable, diversity-guided data race detection framework. It does exactly this enables us to stochastically partially instrument programs across diverse devices and aggregate bug results. The details of how we designed Beanstalk is available in our paper, but an interesting design point here was our choice to use WebAssembly as our deployment vehicle. The reason is it offers this really nice synergy of platform and language agnosticity and a tiny resource footprint that is useful for embedded deployments. So with Beanstalk, we deployed this on a heterogeneous cluster developed in our lab consisting of 21 devices ranging from more powerful x86 edge devices to much weaker, low-power RISC-V and ARM boards. We deployed 8 benchmarks, which are Linux programs compiled to WASM over an interface called Wally, which is actually prior work designed by us and presented at Eurosys this year. I encourage those interested to check it out. We compiled a data set of over 2 million runs of running these programs to evaluate whether diversity at scale is an effective technique. Now, before I get into the bugs we detected, it's useful for us to understand how we evaluate the system. And this is one of the main contributions of our work, which is to propose metrics for statistical bug analysis. The first metric we see is this metric of detectability, which is quite simple. It's the likelihood that a debugger detects a bug. This is a metric that ties in both the bug characteristics and the debugger properties. But sometimes when we want to observe just the property of a bug, we need to remove the debugger from the picture. And this is where we propose 2 more metrics called the observability and the Heisen factor. The observability is the likelihood of a bug occurring when the bug is instrumented. Notice that since we're conditioning on the instrumentation itself, we're removing the debugger from this metric, solely isolating the bug. And secondly, the Heisen factor, which is the sensitivity of this observability across its devices and instrumentation. We have mathematical definitions of this available in our paper, but for this talk, I'm just going to get into what this looks like intuitively with some data. So let's dive straight into the bugs that we found with Beanstalk. We had detectability profiles of 109 bugs found by Beanstalk sorted by this Heisen factor metric. Now, while we haven't gotten to the math, hopefully it's clear to you and you see what this Heisen factor is trying to capture. As we go down the list of bugs, we see that we're seeing increasingly strange behavior. And we in turn also find several interesting patterns. We see these ordinary bugs that happen at low Heisen factors, like we talked about earlier. But we also see these bands of devices, which is quite interesting because it highlights that perhaps having multiple identical devices is actually redundant for bug finding. We also have device and instrumentation specific bugs that are only detectable at specific device and instrumentation operating points, and also completely random bugs that are only detectable at certain points without any perceptible pattern. But then we ask ourselves, why is it that bugs are detected this way? And this is where the observability comes into the picture. What we see from analyzing our data set is that most bugs exhibit highly non-uniform observability. What do we mean by this? If you look at these first bugs that are sorted by increasing Heisen factor, you see that most of these are uniformly observable in their observability. What that means is that there's no statistical disproportionate advantage to debugging across any device or any density. But most of our bugs actually show a highly non-uniform observability. What this means is that we have a disproportionate advantage to debug at these specific peaks of observability. The second thing we notice is that most rare bugs are actually heisenbugs. And so if you look at this top left quadrant that we've highlighted in our graph of Heisen factors and best conditional observability, what you see is that there's a high density cluster of low observability, high Heisen factor bugs. And just to show you an example, you can see that some of these are indeed quite rare and weird in properties. So using this, we would try to actually look at whether diversity at scale will help. And so we ran debugging campaigns with Beanstalk diversity testing and our baseline, which is our null hypothesis of max instrumentation across homogeneous platforms. We ran 10,000 simulations with a fixed compute budget, and we got this plot of a CDF of all of the detection probabilities of bugs found. Now, the interesting thing here is to focus on the third zone labeled here, which are the rare Heisen bugs of less than 0.3 proportion detection probability. And what we see is that actually non-diversifying makes most rare bugs undetectable. We see that only Beanstalk is able to capture these cumulative probabilities up to 0.3, which means that diversity is essential for catching these bugs. And as a result, when we ran these, we also found that diversity improved debugging at these fixed compute budgets. Beanstalk is just able to outperform the homogeneous baseline that we considered, just because it's able to capture these rare Heisenbugs that the baseline couldn't. And we have extended results for these available in our paper. But the main result that we want to highlight is that diversity at scale can work effectively under max instrumentation. So here we see that we can limit the amount of max instrumentation available to Beanstalk and still get performances that outperform the baseline. By just diversifying within, say, 20% of instrumentation density, we see that we can outperform the baseline purely from diversity. And we see similar results for most of our benchmarks. And to conclude, I would like to highlight that this idea of partial instrumentation and diversity at scale don't just apply to data races that we considered with Beanstalk. This is a generalizable methodology. We could apply it across a range of non-deterministic program analysis, think taint tracking, performance bottlenecks, memory management bugs, or even physical I/O bugs. And so with that, this is how I envision the future of embedded debugging at scale. We run our static analysis tools initially on our programs before deployment, run our hardware in the loop simulation testing, but instead we should use diversity testing with full range of instrumentation when we run its simulation. Unfortunately, we can't do this at deployment, but what we can do is run this in the wild across millions of devices with bounded max instrumentation that can be driven down to extremely low rates of maybe 0.1%, since you're scaling across millions of devices. And using diversity testing, hopefully you can find bugs, scavenge for these bugs in the wild, and report bug patches back that could be used to fix your original source code. And so with that, I put up a link to my paper and dataset, and I'm happy to take questions. Thank you.
While you find your questions, might you have kind of a categorization of the 109 bugs that you found and kind of what type of issues they were? Are they race conditions? Are they kind of other types of bugs?
Yeah, so the Beanstalk system we built was using data races as a concrete example. So the 109 bugs were data race bugs. They were captured from known benchmarks that have data races, some handwritten benchmarks. But the idea in general was just to evaluate this concept of diversity at scale. And these were just data races, but we think you would see similar trends with other bugs that I just pointed out.
So hello, thanks for your talk. So after catching the data race in your deployments, how do you reproduce it back when you want to do the bug patch?
So that's interesting. This part is basically looking at actually identifying it. There are several tools in research now for scheduler-directed algorithms. This is not something we did as part of this work, but the idea is once you have the instrumentation, the points, the instructions that actually race, you could use one of these scheduler-directed tools to actually reproduce it.
Yeah, but in order to have a low overhead, you cannot really capture the traces or more information, I guess.
Oh, but once you actually have the bug that you detected at deployment, you at least know where this bug is occurring. So if you want to reproduce it, that's sort of not what we did in our research here, but you could use other tools because at least now you know where the bugs are.
Oh, okay, thank you.